All right, everyone, welcome to lecture 3 of E54. We're going to continue talking about the structure of materials. And first I wanted to show you, this is what I thought was a pretty interesting example from Scientific American. It's talking about how graphene, which you probably have heard of, which is a 2D layered form of carbon. So it's a way we can arrange carbon in a lattice, but just a two-dimensional lattice. Is the building block for many of the carbon structures that we see out in the world. So graphite is a really simple type of carbon structure. And the way we make that is we have these layers of graphene and we stack them on top of each other, showing 1, 2, 3 as we move down on the page. A carbon nanotube is just a layer of that graphene that's taken and sort of folded onto itself to make a cylindrical shape. And a buckyball is just a layer of graphene that is taken, folded to make a ball-like shape. Okay. And this is a little bit different. One of the other ways we can have carbon arranged is in the diamond structure, which is three-dimensional. We also introduced our 3 basic types of metallic crystal structures. We had, we had a few. We had a simple cubic, body-centered cubic, face-centered cubic, and hexagonal close packed. And we said that those last 3 were the ones that we really see out in nature quite often. I just wanted to show a different view of that FCC stacking. This is showing the 2-dimensional picture of how we build up that ABC type of stacking. So the green atoms right here are our first layer. They're close packed in that plane. We put atoms on top at B sites. Now we could go back to the original A sites, or we could go to C. And if we form FCC, we want to take that second choice there and form this 3-dimensional structure. This is just showing a different view. This is that picture of the face-centered cubic that we were used to seeing with the cube drawn over top of it. But now those 3 different planes, that green, that blue, and that orange plane, are colored so that we can see that a little bit better. Do the same thing and see another view of the HCP stacking. So again, in the 2D, we have our bottom layer is the dark green, our middle layer is blue, and then our third layer goes right back on top of the first. So it's we colored it light green, and this is just that 3-dimensional picture showing those same colors there. Okay. So same thing we saw before, just slightly different views so that we can get used to it and feel comfortable with it. I also wanted to go over an example of calculating a planar density. So let's look at the body-centered cubic structure. In this case, it's iron. We can take and see that cube in there, see we have an atom in the center and also atoms at the corners. If I wanted to know what the planar density was along the 1, 0, 0 plane, that would be something like the front face of this cube. So I could draw that 2D projection. I'd have atoms on each of those corners. And I would also need to know something about the element size. Here I would need to know the atomic radius of iron. Okay. So the planar density is, again, what's the number of atoms per unit area. If we look at this box that we cut, there's sort of 4 atoms that are sitting near or at those places, but the whole atom isn't inside that box. In each case, we only have 1/4 of the atom inside that red box. So we have 4 atoms, but only 1/4 is inside the box. So that's a total of 1 atom in that repeating unit. And in this case, the area is just going to be A squared times those for those unit cells. I didn't give you what the lattice constant was. I gave you what the atomic radius was. So what we'd actually have to do is replace that A by some relation connecting it with the radius of the atoms. And we did that in our last lecture. So if you want to look up that relationship, you can. But in any case, if you start plugging in numbers, you can end up with something like you have 12.1 atoms per nanometer squared, or 1.2 times 10 to the 19 atoms per meter squared. Here's a similar calculation for an FCC, or sorry, a BCC structure, but we're going to look at a different plane. In this case, we're going to look at the 111 plane. So this is something that cuts diagonally through that unit cell. Here I'm trying to draw it so we can see where it hits those atoms. So in the BCC structure, this 111 plane hits those atoms along the corner. And this is showing that picture for a larger slice through there. The blue atoms are the ones that are on the plane that we cut. In this picture, the green atoms are one plane below and the red atoms are one plane above, just so that we can see the more three-dimensional structure. So when we take and look at a planar density of some slice like this, we need to make sure we're looking at a two-dimensional repeating unit. So if we just took that triangle at the bottom left here, that wouldn't be a repeating unit because I can't just translate that through space and fill all of the space that my material takes up, okay? So instead, we actually need to have this little sort of rhombus type of shape here. So two of those triangles. And this shape you see, we can move over and find another one just to the right, another one above and to the right, and we could go in and move through space using that unit, okay? So that's our little repeating unit. First thing we can do is find the area of that unit. We're just gonna take that A and that H. We're gonna use some simple geometry to figure out what it would be in terms of just A, okay? We don't need to go over that. That's something you could look up either in a book or on the internet. We'll replace that A with the relationship with the radius of the atoms. It's the same one as before. And we'll find that we have some mathematical relationship with some fractions and then R squared for that area. We would need to think about how many atoms are there per repeating unit, okay? So again, we have the 4 atoms on the corner. In this case, we see that it's actually 2/6 of the atom are inside that box. Same thing with this bottom right, so that's 4/6. And then 1/6 and 1/6. So total, we still have 1 atom in that repeating unit, okay? So notice when we talk about the planar density, we're not talking about, even though I drew those atoms to let us see the repeating units in and out of the plane, if it's not in that plane, we don't care about it, okay? So we're just talking about those blue atoms. And finally, we can plug in what the area is and see that the density is something different. It's actually less than what we had for the 100. That was 12 atoms per nanometer squared. This is 7 atoms per nanometer squared. So those are types of calculations you could be asked to do with a density of your material. Okay, so it's nice that we know those 3 common crystal structures and also that 4th one, which is simple cubic. But not all materials form these types of structures, so we need to relax those limitations. We'd only talked really about highly symmetric systems up until now. But in reality, you can have different lengths of the sides of this repeating unit and also different angles inside to describe this box, okay? So cubic is really the simplest case. It's where all the sides have the same length and all of the angles are 90 degrees. For example, we could start to relax some of those and say, well, the sides could have different lengths, but the angles could still be forced to be 90 degrees. This is an example of something called orthorhombic. In contrast, you could go and start changing what the angles are. And this is showing a picture of hexagonal, where 2 of the dimensions are the same, 1 is different, and then you have some 90-degree angles and some 120-degree angles. So you can actually go through and find that there are 7 basic crystal structures that we could come to looking at unique symmetry elements. And this little table shows each of those. So on the top left is the most symmetric one. So all the lengths of the box are the same, all the angles are the same and equal to 90. And as we move around this, we start to relax some of those considerations. So for example, we can find what's called a tetragonal cell. This is where 2 of the sides are the same, 1's not, but all the angles are still 90. Okay. If we get to the bottom right, this is the sort of other end of the extremes. In this case, triclinic is what we call a crystal structure that has all of the sides are different and all of the angles are different and none of them are 90 degrees. This table right here is showing some of the same information. So our 7 crystal structures here, how we would describe them, what their angles and axes lengths are, and finally what the volume of the unit cell is. And all I want to point out here is that it's very simple to see when all the angles are 90, we just multiply the side lengths by each other. Once we're getting a little bit more complicated and we can have tilted and shifted unit cells, we have to start to account for those different angles. But it's just geometry. It's not sort of incredibly hard there. Okay, so we can take those different types of crystal structures and think about having unique lattices. And what we mean by that is we take that basic crystal structure, which just talks about how long are each of these sides and what are the angles, and start putting atoms at different places. So for example, in this top row, these are all cubic crystal structures that we've seen. Simple cubic is just putting atoms at the corners. Face-centered cubic is putting atoms at the corners and the faces. And body-centered cubic is putting atoms at the corners and in the middle of the body. Okay, so we can go through and do that for all of those different options that we had there. Okay? And one thing is that you don't see these same three options for each of those different crystal structure types. So for example, for tetragonal, we only see simple tetragonal and body-centered tetragonal. Okay, the reason that happens, the reason, for example, we don't see face-centered tetragonal, is that you can make a structure with those same features. Some of the sides are the same, the height is different, and the angles are all 90 in an easier way by putting an atom at the center than you can at the face. So they're equivalent. So it would be redundant to say face-centered tetragonal. Okay? And we can work through and do that for many of the other ones. You see that some of them have more options than others. For example, orthorhombic has a lot of options. Hexagonal doesn't. Hexagonal, we don't really see those different options. Hexagonal by itself is sort of the interesting structure. I want to make sure we review crystallographic coordinates. We talked about this a little bit at the end of our last class, but it's pretty important. So we want to go over it again and make sure we're on the same page. So we're often going to need to look at some structure like this. This is showing something that has sides of different lengths and different angles. Before we had a very simple cube, so it's easy to visualize, but it doesn't change our procedure at all. So if we want to talk about some point P inside of this box, even though it's not a cube anymore, we do it in the same way. We just count out how far we have to move along each axis. So we would have to move a distance Q along the x-axis, a distance R along the y-axis, and a distance S along the z-axis. So this is exactly the same. It doesn't matter that those axes are not at 90 degrees from each other anymore. And we would describe it by the coordinates Q, R, S in this case. If we want to put sort of specific examples on that, we can put some side lengths on that box. None of them are the same. And if we move, for example, 0.12 along the X, we're actually moving 1/4 distance in that X unit cell. We might move 1 full period across the cell in Y, and then 1/2 of the way up Z. Our position P would be 1/2, 1, 1/2. So just as a reminder, we can do the same thing and talk about directions. We're going to talk about finding a vector, which describes connecting our origin to that point that we're talking about. And again, they're just projections along our X, Y, and Z axis. These are the same directions we talked about in our last class. So for example, 1, 0, 0 would be just along that X axis. 1, 1, 0 has an X and a Y component, but no Z component. And 1, 1, 1 has equal components in the X, Y, and Z axes. Okay. So one common thing we do that we didn't talk about last time is that we often want to multiply or divide by a common factor to reduce this to the smallest set of integers. And just as an example of that, let's look at this specific box on this bottom. We want to describe this green arrow right here. So we can see that it moves 1/2 of the distance in X, 1 of the unit cell in Y, and has 0 movement in Z. So we'll have 1/2, 1, and 0. It's more common that you'll see this drawn, even though if I were saying, where's this point is at 1/2, 1, 0. Usually when you talk about the direction, you want to say that it's 1, 2, 0. Okay? And then you put it inside of your square brackets if we're talking about a direction in this case. One other sort of detail to mention is it would get a little bit clunky to put negative signs if we had a movement in the negative direction. So in this example of this green arrow here, we're moving 1 unit cell in the X, -1 in the Y, we actually show that with what's called an over bar. So it's 1, 1 bar, 0. And that just helps us see that these are numbers that are separated from each other, not some sort of equation or mathematical operation. Another quick point we need to talk about is that basic idea of describing things in terms of XYZ coordinates is simple and it works, but it only works when those coordinates are all independent of each other. An interesting complication comes up when we talk about hexagonal crystals. This is showing that hexagonal structure that we use to describe the HCP structure. We have usually 3 axes that we use in this closed pack plane. So A1, A2, and A3, and they're all separated by 120 degrees. And then finally, we have Z in that vertical direction. The issue is that we have a plane or a 2-dimensional piece, and we have 3 axes to describe it. So what that means is that these 3 axes cannot be independent of each other. We have to find, there has to be some equation that relates them. And you could define it in different ways, but the way we're going to do it is we're going to say that A3 has to be equal to negative A1 plus A2. Okay. The effect that has is it gives us a rule when we're describing directions in hexagonal crystals. We have to make sure that when we describe them, we're going to call it HKIL. So this is A1, A2, A3, C. Often C is that Z axis. We have to make sure that H plus K is equal to negative I. And you can think of it, this is just a rule to enforce this condition above. Okay. So we can have a procedure to follow. I'm going to show you this example right here. So in this case, we have this little green arrow shown. I've already shown you what the answer is, so you know what it is ahead of time, but let's work our way through it. So the first thing we need to do is make sure that this vector is positioned so it starts at our origin. That's already done here, so we're okay. We can look at the projections in each of those directions, but we have to make sure now that we're adhering to this rule. So for example, the easiest way, if we didn't have that rule, the easiest way to make this green arrow would be, say, we're moving 0 in A1, 0 in A2, -1 in A3, and 0 in Z. Okay, but that would be 0, 0, -1, or 1 bar, 0. And that doesn't fit my rule, okay? So I have to find a different iteration that does. So it turns out that if I move 1 unit in A1 and 1 unit in A2, I end up back in line and form that straight green line, okay? Now, I still have to fit my rule. So 1, 1, 0, 0 wouldn't work either. That doesn't fit our rule, but we're in the right direction. So what I can do is, since I'm here now, I can move -2 in the Z, and I end up having moved far enough, okay? So I move here, I have to move a little bit more, okay? So if I take that point, I can kind of, this is just drawing you to show what I was just mentioning in the 3-dimensional picture. So we move A1, we move a distance A2, and we also have to move some in negative A3. Okay. This picture on this slide is just showing some other examples. We can have simple things like this purely vertical direction is just 0, 0, 0, 1. It doesn't even care about those A axes. But finally, we can have other important ones. So 1, 1, 2 bar 0 is something that's along these axes. Usually, if we're talking about HCP, we'd have an atom here and an atom here. So it'd be atoms touching each other. In contrast, if we want to have an arrow that's pointing out one of the faces of this hexagonal cell, it could be something like 1, 1 bar 0, 0. Okay. We could come up with other examples on all of these faces. So let's do a practice problem really quick. So I have a few different arrows plotted on here. And I'll ask you, what's the number for this vector A. This is that green arrow. Okay. I'll give you 1 second, and then I'll start to explain. So if you want to do it yourself, pause, and you can write it down. Okay. The first thing to do is imagine that this was our origin and think about how much we are moving, okay? So if this is our origin, how much are we moving in the X direction? Well, we're moving forward 1 unit cell. So it's a 1. We're moving to the right in that Y direction, 1. And then we're moving down 1/3, okay? So we have 1, 1, and negative 1/3, right? The last thing we need to do is we can't have fractions in there. So let's multiply the whole thing by 3. And that means we'll have 3, 3, negative 1. Just as a reminder, we talked about how to find plane notations in our last class. So for example, if I want to talk about this shaded yellow plane here, I need to go and find the intercepts. The reason I chose this example is the procedure I told you last time. Find the intercepts, take the reciprocals. If you have to reduce it, that's good. That's pretty easy. But oftentimes people get confused in in a few specific cases. And one of them is when either the plane intercepts the axis itself or it intercepts the origin. Okay. So the problem is I want you to tell me the intercept, but it's hitting this whole axis. So does it hit that at x equals 0? Yes. X equals 1/2. Yes. X equals 1. There's really no way to define one place where it hits. So this isn't a good choice of our origin. You can actually see the same thing on Y and Z because it's telling us that it hits it at 0. What's the inverse of 0? Well, we'd end up with infinity. Okay, it's not some crazy physics conundrum we ran into. It's just a bad choice of the origin. So we actually want to do, if any of those things happens, is we're going to say, instead of being at this back left point where my cursor is right now, we're going to choose this other origin as our new origin. Okay, so now it becomes a lot easier. So where does that plane intercept that x-axis? So this is my new x-axis. Well, it doesn't. It would never hit that. So it's going to be at infinity. Where would it hit the y-axis? Well, it's going to hit it at -1. Okay, so I can plop that in there. And then where does it hit the z-axis? It hits at 1/2. I could take that and do the reciprocals. So I end up with 0, -1, 2. So I have a 0, 1 bar, 2 plane. Okay. This isn't really so much a trick as it is just recognizing what we're doing here. We're trying to describe a plane inside in reference to this unit cell. But remember, the unit cells are sort of repeated all through space. This is just that smallest unit that can describe my structure. In a real material, there's going to be another unit cell next to it with atoms, another unit cell next to that with atoms, and so on and so forth in all the different directions. So I should be able to define it in all of these different directions without a major problem, okay? You could pick this one right here, okay? And I'm going to do that real quick. Let's say, what if our origin was right here? Where does it hit the x-axis? It never does. So our intercept is infinity. Where does it hit the y-axis? It hits at -2. Okay. And where does it hit the z-axis? Well, now it would hit at 1. Okay. We'll take the inverse of that. We end up with 0, -1/2, 1. We can't have a fraction. We need to multiply that whole thing by 2. We end up with 0, -1, 2, the same plane index. Okay, so you should be able to find the same plane index even if you change your origin around in different ways. If you want a sort of weird example, make your origin up here and try to guess what it would be. You can get there. It shouldn't change if we think about being in different unit cells. So here are another few examples of Miller indices, just to, if you want to sort of practice and try it yourself. This one is slicing through that structure. You can see, okay, here it hits x equals 1/2, y equals 1, Z is infinity, take the inverse, we end up with 210 plane. This is also showing some different ones. We've seen things like the 111 plane. These are those cuts through that middle of that cell. This is also showing the 111 bar plane. So it's just cutting through the cell in a similar way, but sort of oriented in the other direction. So I see these ones as sort of facing up and to the right towards me. These ones are facing back and to the left away from me. One important thing to point out is that you can make a distinction. So 111 and 222 planes are really the same because we should reduce 222 down to 111. But in this case, these are actually two different families of planes. So the 010 planes are hitting on the outside of the cell. And the 020 planes are hitting on the outsides of the cell, and also there's one in the middle, okay? Those aren't technically the same thing because I can't divide this by 2. If I did that, I'd be trying to do 0 divided by 2, and that's not a logical mathematical thing to do, okay? So just, if you see those, that is okay to have that happen. Again, we can talk about specific directions and specific planes as well as families of planes. What I'm just showing on this image here is that we can talk about specific 100 type planes. So this front is 100, the side is 010, the top is 001. The left side of this cube is 0, -1 or 1 bar 0. Back is 1 bar 00, and the bottom is 001 bar. But I could say these are all the 100 type family of planes. Okay, and all I have to do that is change my bounding symbol. This is just showing another example of how we could do planes for the hexagonal systems. You really take the same type of procedure. What are the intercepts? And then we'll flip them. Again, remembering to keep h plus k equal to -I. And on the right here, I'm just showing some very common planes that people care about in the HTTP system. So this bottom plane is 0001. That's the one on that closed pack plane. The face of this hexagonal cell is a 1 bar 010 plane. And this cut through this cell at some inclined angle is a 1 bar 1 plane. So let's ask ourselves the question, just to quickly test ourselves, what is the index of this shaded yellow plane? Okay, if you want to do it yourself, pause and start up after you did the work yourself. Okay, so we need to define what where we're going to intercept these different planes. Sorry, I accidentally hit the button, my bad. And what we can do is see where we cross that plane. So for A1, it's very simple. It's 1/2. Okay, so it's hitting that at 1/2. This would be 1. For A2, it's relatively simple. It would be -1. So if I extended this forward and back, I can see the plane hits here. If I extended A3 forward and back, I can see that it's going to hit at -1 as well. And it's going to be infinite for Z. So 1/2, -1, -1, infinite. We take the reciprocal of that, and we end up with 2 1 bar 1 bar 0. And we should double check and make sure that that fits our rules. So 2 plus -1 is going to be equal to 1, and -1 times 1, or sorry, 1 times -1 is going to be equal to -1. So we fit the rule. We're all good there. So these different planes we just talked about aren't some obscure thing and some exercise in geometry. They turn out to be really important for how materials behave, but also how they form. And a cool way you can see this is looking like you were to go to a natural history museum and look at the different types of minerals they have. They often have a shape that is connected to those specific planes inside of the structure. Okay? So this crystal right here is formed a hexagonal shape, but there's also some facets on these corners. This one right here is a chunk out of something that had a relatively cubic shape, although there's some facets on the corners. These type of structures happen because certain planes have lower energy than other planes. Okay? And just like we said when we talked about two atoms and their distance away from each other, we said they wanted to get far enough at this sort of perfect distance so that their energy was minimized. The same thing happens when we form a crystal. It wants to minimize its overall energy, and it wants to have big planes or surfaces of the low energy facets. Just as another example, on the right is a crystal structure with a hexagonal crystal structure. So it forms these hexagonal chunks. And this one has something that's cubic. So it forms a cubic shape in the bulk as well. Okay, so these things are big. These are things you could hold in your hand, so they're centimeters or inches if you like. But those properties of how the atoms want to organize on the nanoscale are affecting this bulk behavior. As another cool example of this, I found this paper where these authors were talking about trying to find and make near spherical salt crystals. And their motivation was something that is practically very important. It was that if you're thinking about how granular materials move, you often need them to flow through some sort of device. And in this case, they would like to have spherical particles so they could roll and move and shift past each other very easily, rather than get locked up and maybe clog some injection device or something like that. And what they were doing is trying to solve this issue where if you just take a piece of salt, it might have this cubic shape because it has these 1, 0, 0 type of surfaces. And what they did is they put in the presence of some chemical, this glycine, and what it did was it changed the relative energy of those faces. So in this case, it promoted, rather than 1, 0, 0 type planes, it promoted 1, 1, 0 type planes. And the idea here was pretty simple. It's that if you have 1, 0, 0 type planes, you can just form this cube, and that would be your bulk piece of salt. If you have these 1, 1, 0 type planes, you'll instead form this shape with these angled sides, which is called a rhombic dodecahedron. And if you look at that in an electron microscope, you can see those different facets that they were predicting, and this lets these salt particles flow better. It's important to point out that you can get changes in your crystal structure by looking at different atomic systems, but even for the same atomic system, if you change external variables like your temperature or your stress, you can get a crystal structure change. A good example of this is tin. So if we take tin, we can find it in the what's called a beta structure or a white tin structure. It's this cubic type structure where it has atoms on the corner, and then there's the atom in the center. If we cool it down, we'll find that it forms something. This is actually called a diamond cubic type structure, which we'll talk about later. But this fact that you have this crystal structure means that the density, so atoms per volume or atoms per plane, per area of different planes, is changing quite a bit. And for example, if you have some part like this and you can heat it and cool it, it might want to expand or contract when it has that change in the crystal structure. And if it can't do that efficiently, it can crumble and break. You can also see this, another way of talking about this is by looking at things, for example, like toughening mechanisms. So this is an example of a zirconia material, so zirconium oxide. And there's a crack here. And what people found is there was this really interesting mechanism that would let the material deform more and absorb more energy before it broke. When you pull on this type of structure, this little crack acts as a stress concentration. So there's really high stresses around that notch. And what you would find is if you went and inspected the materials, you would find that most of this is tetragonal. But if you zoom in, you would get monoclinic particles close to that crack tip. So that tells you that the stress is actually changing the crystal structure near that crack. And zirconia is actually a really interesting one. This is showing different atoms, zirconium and oxygen, plotted on here. You can have a cubic type of structure. You can have a tetragonal where all the angles are 90, but the that unit cell is stretched in that vertical direction. So C is not equal to A. Or you can even have all of these lengths being slightly different, and then the angles being non-zero as well, and have a monoclinic type of structure. There's lots of options there. a name for this where a single system can have different crystal structures is sometimes called polymorphism, sometimes called allotropy. So if we say we have different allotropes of tin and zirconia in this picture. Another good way to see this is in iron. So if we take pure iron at room temperature, it's a body-centered cubic structure. If I heat it up, eventually I'll hit some critical temperature, 912 degrees C. It'll form an FCC crystal structure. If I keep heating it up, eventually it'll cross another critical temperature and form a different BCC structure. And then finally, if I keep heating it up, it'll eventually melt. Okay? But this is relatively common. It happens in titanium. We can form both alpha and beta titanium, so different crystal structures. And then all of those examples of carbon, so things like diamond and graphite, are different polymorphs or allotropes of the same system. So one of the things that we need to take a step back and think about is how these different Bravais lattices come together and can become more complicated. So this picture right here is showing you the different Bravais lattices and sort of assuming something that it's common but not always true. And that's that there's only one atom at these different positions. Okay, so far we've been talking about that, but many times, especially in ceramics, that's not the case. So what happens if we want to put together something like cesium and chlorine to make cesium chloride? We would get a structure that has this cubic shape. There's chlorine atoms at the corner and a cesium atom in the middle. And at first, you might say that this is body-centered cubic. But if you said that, you'd be wrong. So it turns out when we say simple cubic or body-centered cubic, we're talking about these being the different lattice points. But that sort of assumes that all the atoms are the same. You actually make this cesium chloride not by putting atoms at the corner and at the middle. You do it by putting groups of atoms, so 2 atoms at a time. So for every lattice constant, I'm going to put 1 chlorine atom right at that lattice point, and then I'm going to put 1 cesium atom at a point 1/2, 1/2, 1/2 of the unit cell away. Okay, so think of it as we're adding in groups. So when I put this chlorine atom at this top front right lattice point, I actually am putting in a cesium in the middle of the unit cell that's right above this. Okay, so that's important to talk about. So we actually have a simple cubic structure in this case, but we have a basis of 2 atoms rather than 1. Another good example of this is diamond. So if I look at this structure, I'm showing it 2 different ways. On the top left is sort of atoms, so they're big enough they can touch each other. On the right is where they've been shrunk a little bit just so we can see where they're bonding with each other. What this looks like is I have a cubic structure. So there's atoms at all the corners. It's almost like a face-centered cubic. So there's atoms at all the faces, but there's some extra atoms put in. Okay, if I look closely, I have 1, 2, 3, 4 atoms that are inside of that unit cell and are neither on a corner or a face. Okay, so this isn't a totally different crystal structure. This is actually a face-centered crystal structure, but instead of putting 1 carbon atom at each location, I'm going to put 2. I'm going to put, this is my lattice point. I'm going to put 1 there and 1 in by 1/4, 1/4, 1/4. Okay? And the same thing for that atom that I put in at the face. So I'm going to put 1 atom there, but also in 1/4, 1/4, 1/4 from that location. Okay, so this on the bottom here is showing the grouping of how we can insert those atoms. So we're putting in 1 set here, 1 set at the bottom, 1 set at the front face, and 1 set at the left face. Okay, and we could do that for all the cubes around us, and we would build up something with this diamond cubic structure. So this is not some unique structure. It's just face-centered cubic with a 2-atom basis. We'll also eventually talk a lot about something called polycrystalline materials. And I'll just take a second to point something out. We mentioned that all these atoms want to form on these ordered lattices, and that is true. But that's talking about how locally they form. If I look and zoom in on one region of the material, I can see this grid. So think about it as there'd be one atom at each of these lattice points. But it's oriented a certain way with respect to how I'm viewing it. If I move very far inside the material and inspect it again, I would have to see that same structure. So if this is face-centered cubic, this would have to be face-centered cubic as well. But there's no reason that that cube has to be oriented with my viewing coordinates in exactly the same way. In this case, it's been tilted by some angle. Okay. These are what we would call different crystals or grains. And the reason that's important is that there has to be some defect at the grain boundary or the area where those grains touch that we need to start to think about. Okay, so at this point right here, we're sort of through chapter 3. Just a quick summary to remind us what we talked about so far. We talked about how atoms can assemble into crystalline and amorphous structures. So this is crystalline is something with long range order. Amorphous is lacking long range order. Common metallic structures are face-centered cubic, body-centered cubic, and hexagonal close packed. We might talk about things like coordination number, atomic packing factor for different structures. For face-centered cubic and hexagonal close packed, they're the same. And they're actually, the atomic packing factor is the maximum amount we can get for packing atoms in there, okay? One thing, we haven't talked much about their properties, but we'll eventually see that their properties are quite different, okay? Just based on this crystal structure, we can do some things like talk about what's the density of the material, and we could input things like atomic weight, atomic radius, and crystal geometry to get it a firm number. These different crystallographic locations, directions, and planes are important, and we can define linear and planar densities for each of those. This idea we just mentioned that materials could be single crystals where we have one crystal orientation throughout the whole sample or have many of those crystal orientations. And this will come up a lot when we start talking about how we can have anisotropy in properties of different directions. And finally, we talked about polymorphism and allotropy, where we can have different crystal structures for the same material. So the last few slides today, I want to talk about where we start to deviate from these perfect crystal structures. So saying something is FCC and what the symmetry of that crystal is very important. But we also have to consider when we deviate from that. So when we have real materials, they're going to have deviations. And I want to introduce those today. So these are the main types of imperfections or defects that we can have inside of our crystal, and we'll work our way through them, both starting today and then working into some later classes as well. But we can have things that are called point defects. So this is, you can think of this as we're changing what's happening to a single atom, okay? We'll have a few different types of vacancies, interstitials, and substitutional atoms, and I'll show you pictures and what this means. We can also have something where a line of atoms are affected and are different than that base crystal structure. And a good example of this is something called a dislocation. And finally, we also can have area defects. So this is where some planar region of our material is different than that base crystal structure we talked about. And a good example are those grain boundaries we talked about, where two crystals meet. We're going to have a plane of material. It doesn't have exactly the same structure as grain A or grain B. Instead, it has some sort of defect structure. You'll also see these things described by the dimensionality needed to describe them. So 0D defects would be these point defects. So it's at one location in space. It doesn't have a length or an area or a volume, okay? Line defects are what we call one-dimensional defects. So we can just describe how long that dislocation is. And grain boundaries are two-dimensional defects. We can describe an area or something, it's a certain number of nanometers squared, that grain boundary. So let's look at the different types of point defects quickly. So a vacancy is pretty simple. These bluish gray atoms here are a plane in our crystal structure. A vacancy is if we just go in and take out one of those atoms, okay? What is also drawn here is the fact that if we just take out that one atom, the other atoms don't all stay rigidly where they were before. Instead, they're going to try to accommodate and deform to try to fill in that space as best they can. We can also have what's called a self-interstitial. So this is if I took my original crystal structure and tried to squeeze in an extra atom, so one of these extra bluish gray atoms, into some location between the atoms. So everything was happy before, and I squeezed it in and deformed the lattice. And you can see the difference. So in one case, the lattice around it is pulled in, in the other case, it's pushed out. So we'll have different stress states around that defect. This image is just showing how these things can be related. So for example, that atom that was in the crystal structure can move out and form a self-interstitial. Okay. In contrast, if this self-interstitial can find its way to the vacancy, these defects can go away. We can also have impurities. So we can have a substitutional impurity. So these bluish gray atoms here are on some given lattice. And what I've done is I've taken and replaced one of those atoms with a green atom. Okay, so the same crystal structure is everywhere, but locally we have a different type of atom. In contrast, we can also have what's called an interstitial impurity. So this is where we take some atom, it usually has to be much smaller, and we squeeze it into some open region in the lattice, right? Remember I said that even FCC and HCP are only 74% full, so that means there is lots of free space for things to squeeze in there and for these impurities to be in your material. As we have these different point defects, we'll end up having distortions of that lattice. If we remove an atom, so we have a vacancy, all the atoms around it have to pull in and try to fill that space up a little bit. If we put an interstitial in there, all the atoms will swell and be pushed out. If we do a substitutional atom that's smaller, everything will have to pull in a little bit. If we do a substitutional atom that's bigger, everything will have to shift out. And if we have, for example, this is one atom moving into an interstitial position. The thing I want to point out on this bottom right is we've been mainly talking about metallic systems where there's no directionality of bonding and there's really no charge to any of the atoms. When we start talking about these defects in things like ceramics and we start talking about electronic properties, it turns out that we will have a balance between the types of defects, so where the atom's going, and also the net charge of the system. So in this case, there was a negatively charged ion that was removed, so you need to have a positively charged ion removed as well. Okay, the last thing I want to mention is that vacancies are sort of a unique and interesting type of defect. So most of the defects we're talking about are what we would call metastable. So they're a deviation from our low energy crystal structure. So there's an energy penalty for having them. And generally the system doesn't want them. It wants to get rid of them, okay? Vacancies are a bit weird because they have an equilibrium concentration as long as we have a non-zero temperature, okay? And you can think about this with just thinking about what's the free energy of that defect. So when I mentioned we have some deviation from the perfect crystal structure, that energy penalty is called the enthalpy, okay? And this is going to have some energy penalty delta E for each vacancy we add. So if we look at the energy of the system as a function of the number of vacancies, as we add more and more vacancies, so move to the right on this plot, our energy penalty from the enthalpy is going to go up and up and up. Okay, that kind of makes sense. We're adding more defects, it's having more of an energy penalty. That's not a good thing. If we remember that the system wants to find the lowest energy state, this by itself would say we don't want any vacancies in our system. But that's not the only part. So the free energy of the system is both the enthalpy plus an entropy term, negative TdS. And it turns out that this can actually be negative. So if we add in more vacancies, we can actually decrease the energy of the system through this entropy term. Now, the free energy is the combination of these two. So the total system energy is actually going to look something like this. So eventually, if I add enough vacancies, that enthalpy term takes over. but there is a local energy minima, and it's not at 0. So it's at some amount n star. So for a given temperature, we'll have a given equilibrium vacancy concentration. And you can do a little thought experiment. What happens if I increase my temperature? Well, if I increase temperature, I make this term more negative, and it's going to push this minimum out further. So it means as temperature goes up, I should have more and more vacancies in my system, which is pretty cool. We can actually describe this with something called an Arrhenius equation that we'll see many, many times in this class. Okay, so this is describing how the equilibrium concentration of vacancies changes with temperature. On the left side is a fraction, which is the number of defects divided by the number of potential defect sites. So what fraction of my material is vacancies? And on the right side is an exponential term, which has a negative activation energy, and it's divided by Boltzmann's constant and temperature. Okay, this term in here has to be unitless. So the bottom has to end up having the same units as the top, so that when we divide them, they get rid of it. It's unitless, which makes sense because we're trying to look at a fraction which doesn't have units either. So your choice of Boltzmann's constant, it can either be the value which is joules per atom Kelvin, or electron volts per atom Kelvin. It just depends on what units you use for that activation energy. So what you can do is go and do an experiment, for example, and say, I'm going to take a material, I'm going to measure how many vacancies are in it as a function of temperature. So as I increase temperature, vacancy concentration goes up. This could be real experimental data I'll get. I could see that exponential dependence. And if I take this and replot it, I can go and find, okay, if I do a log plot on the y, or sorry, log axis on the y and inverse temperature on the x, the slope of this linear plot is going to be related to that activation energy. So oftentimes this is really important for figuring out what's the mechanism behind something like this. In this case, it's going to be the formation energy of these vacancies. So that's a kind of problem that I could give you. I could say, well, I'm going to give you a given set of material. I want you to find the number of vacancies in 1 meter cubed of copper at a given temperature, 1,000 degrees C. So it's actually quite a big chunk of material. I just did it to simplify the math, okay? And I would give you things like, okay, what's the density of copper? What's the atomic number of copper? And the idea here is you're trying to be able to find what's the number of atoms per centimeter here, trying to do a conversion. In this case, I gave you the activation energy rather than take it from an experiment. And I also just remind you what the Avogadro's number is. So the first thing we want to calculate is what's that fraction of our material, which is vacancies. And that's that exponential. You were given the activation energy, so we can plug that right in. The Boltzmann's constant is given, and then we have to put in the temperature. The one thing I want to point out here is whenever we're calculating things with temperature, you have to make sure to use an absolute temperature scale. So Celsius is somewhat arbitrary. It was chosen so that 0 is when water freezes and 100 is when water melts. That's great, super useful, but that's not absolute temperature. So what we actually have to do is put this in Kelvin, okay? So it's not 1,000 degrees C, it's 1,273 Kelvin. If we plug those numbers in, we'll get that this fraction, so the fraction of vacancies we should have is 2.7 times 10 to the negative 4. The question actually asked you for the number of vacancies. So what I need to do is solve for this n sub v here. And to do that, I need to figure out, well, how many atoms are in 1 meter cubed of copper? So to do that, I can basically just figure out and take my different descriptions. So it's the density multiplied by the number, Avogadro's number divided by the atomic number times the volume. And I'll end up with, we have total 8 times 10 to the 28 sites. Okay. To get to the total number of vacancies, we can just multiply these numbers and get that we have 2.2 times 10 to the 25 vacancies. So this chunk of material is going to have not thousands, not billions, some number I don't even know what the prefixes in front of that number of vacancies, so 10 to the 25 vacancies. So you can actually have quite a bit of vacancies in your system. Now, one sort of caveat and a little trick I did is I chose a really high temperature for copper. So this is actually pretty close to the melting temperature of copper. So, but the point remains, you can end up with many, many, many vacancies in your system, and this is at equilibrium. They're not defects that want to go away. One cool thing is that you can actually go and see this. This is a video taken. It's a low energy electron microscopy video of, this is nickel aluminum, and it's a specific surface of this. And what they're doing here is they're increasing the temperature and watching what happens to this surface island. And as you increase the temperature, you see that the island grows. As you decrease it, you see that it shrinks. Increasing it, watching it grow, decreasing, watching it shrink. And the reason that happens is as we increase the temperature, our vacancy content or equilibrium vacancy content inside the bulk is going to be higher, which means we need to have atoms, which were originally on lattice positions, come out. Okay, so if I want to form a vacancy right here, this atom needs to diffuse out to the surface. As it gets there, that island gets bigger. Okay, just thought that was a pretty cool way to see this. You can actually see that vacancy concentration resulting in the size of this surface island here. All right. All right, thanks everyone. This is the end of lecture 3. I will see you all soon in a question and answer session.